Hello folks, and welcome to my OpenXR Masterclass. The plan for the talk today is to spend a few moments introducing myself, introducing OpenXR, and looking at OpenXR as a standard in context, what it is and isn't. Then we'll take a deep dive into OpenXR application structure and API usage. And we should have time for question and answer at the end. My name is Ryan Pavlik. I've been working in the VR realm since around 2009. I've been involved with the OpenXR working group since the first official meeting in 2017. I was elected specification editor for the OpenXR working group in 2019. My job currently is as a principal software engineer at Collabora, where I work on the XR team and work as a developer on Monado, which is our OpenXR runtime. So what is OpenXR? Well, OpenXR is a royalty-free open standard that provides high-performance access to augmented reality and virtual reality, so AR and VR, or XR collectively, platforms and devices. The provisional release 0.90 was released at the Game Developers Conference 2019 in order to publicly show progress and seek feedback. We released version 1.0 of the specification at SIGGRAPH in 2019. The 1.0 release defines an interface between an engine or application and a runtime and the required behavior of a runtime. It does not control the interaction of a runtime and underlying devices. I'll get to that in a moment. Like many Chronos standards, conformance tests are a part of the package. Runtime conformance tests and adopter program are forthcoming. That's one of the main focuses of the working group at this time. As I mentioned, the 1.0 specification includes the interface to the application with a compatibility promise that comes with 1.0. So now is the time to start building applications on top of OpenXR. 1.0.x patch releases are minor changes that fix spec bugs or add extensions. These are typically released on Fridays. My general rule of thumb is that if there's a specification change or extension changes that are in the Khronos private GitLab instance for a given week, I will typically cut a patch release for that week. So the time between patch releases can be variable, but I work to get whatever the working group has put together out as quickly as possible. Now, if you go to the Khronos website or look around at some articles, you might see mention of a different diagram that has a device layer, which would allow a single runtime to connect to multiple XR devices. The diagram at the right is a more accurate description of the current 1.0 ecosystem. There's no standardized interface between runtimes and XR devices. There's no device plugins, but runtimes may support one device or more than one. And importantly, the interface between an application and the runtime is standardized, so you can use your applications across multiple runtimes and thus multiple devices. There's no public estimated time to have the device layer as in the statement of work and the marketing materials ready. As I mentioned earlier, the main focus of the working group at this point is finishing up the conformance tests. We're also very interested in promoting uptake and adoption of the new standard. Khronos is a nonprofit industry consortium that brings together the major players in technology fields to put together independent open standards. These standards started with OpenGL. They took over for the ARB. The collection of standards has now expanded widely. A commonality between many of the standards is that extensions are a key part of the design. There's a core API, and then there are extensions that can be added at an independent pace and implemented by one or many vendors that allow new features or vendor-specific features to be lit up selectively on systems that can handle them without impacting the portability of software. Like all Khronos API standards, conforming runtimes that run the conformance test and pass it and complete the other requirements of the conformance and adoption program receive patent protection and trademark licenses per the IP framework. Take a look at these slides. That is linked. I am not a lawyer, but this framework makes Khronos the place where the big players in industry in these very highly competitive tech fields can safely get together, talk about things, and come up with standards that will work across all of them. Like other Khronos standards, OpenXR is royalty-free. In terms of relatives of OpenXR, the conventions and style and even some of the nitty-gritty, such as the tools used by the working group, are strongly influenced by Vulcan. Vulcan is a low-level, high-performance rendering and computation API, primarily for use on GPUs. We have a mostly shared toolchain for generating specifications. We have similar development and release practices. Like Vulcan, we have a loader with support for API layers, which let you hook any function in the API in a controlled, understandable way. However, just because OpenXR takes a lot of its practices from Vulcan does not mean that it's exactly like Vulcan. OpenXR is rendering API neutral. So despite the fact that there are some Khronos rendering APIs, OpenGL, OpenGLES, Vulcan, there are also non-Khronos rendering APIs, the Direct3D family, that are also supported by OpenXR. All graphics API support are in extensions. All these extensions are designed to work similarly, despite the fact they're working with different rendering APIs. One major design difference between OpenXR and Vulcan is that OpenXR is a lower frequency API. So you're not executing hundreds or thousands of OpenXR calls per frame. You might have a handful of calls. Eliminating all argument checking overhead is not necessarily required for performance in OpenXR. As a result, runtimes for OpenXR are required to detect nearly all invalid usage and return an error code. In Vulcan, there's valid usage that is only checked by the validation layers, and if you pass invalid usage, there may be undefined behavior or unspecified behavior by the driver. Whereas in OpenXR, we have a validation layer. It provides useful information, but most invalid usage also has an error code that would get returned, and that is required by the specification for the runtime to return. Of course, there is some risk of undefined behavior because it's a C API, but this minimal risk can be reduced by a language projection or wrapper that makes it more difficult to misuse pointers in a way that would break things. Additionally, OpenXR is a much smaller spec. It's only about 300 pages in PDF format. We've also learned some lessons from Vulcan. We've talked with the folks on the Vulcan working group and asked them what lessons they wish they had learned. In our case, one of those is that the loader, which is responsible for finding the runtime and getting function pointers, our loader ships with applications and not the system or the driver on Windows. On Linux, it's tentatively system-wide because there are distribution-specific ways of controlling ownership of the loader. As of recording this on April 14th, here's the current availability of OpenXR runtimes. The Microsoft OpenXR runtime is available for both Windows MR HMDs as well as the HoloLens 2. Additionally, the Windows MR runtime does work with the Windows MR simulator mode, so you don't need hardware in order to run that OpenXR runtime. Oculus has a runtime that they're prototyping in the public test channel, and an SDK for that desktop runtime is forthcoming per their announcement at roughly would have been GDC time 2020. And recently the Oculus mobile OpenXR SDK, so that would be for Quest primarily, is publicly available in a preview form. If you're using Linux, you can use the Monado runtime, which is an open source project led by my team at Collabora. It works on multiple different devices and is in active development. Note that because conformance tests are not yet finalized and published, and therefore there are no conformance results, these are all technically preview implementations, but these should be useful in order to get you started developing with OpenXR. This is the structure of an OpenXR app. We'll go into all of these in more detail. You first get started by configuring and creating your instance. Next, you find out where and how to run. This involves looking up a system ID atom and using the view configuration type enum. Then, you set up your interaction. In OpenXR, this is done using action sets and actions. Finally, the last setup step is preparing the immersive experience by creating your session, attaching action sets, creating reference and action spaces, and creating your swap chain. Then, the frame loop handling input and events is the body of your application. There are a number of object or handle types in OpenXR that are important. These are the main handle types and shows as well which handle types are their parent. In OpenXR, destroying a handle parent also destroys that handle. So if you destroy a session, that also destroys those associated spaces and swap chains. And if you destroy the instance, that destroys all of these handles, since they're all derived from the instance. In addition to handles, there are two additional types known as atoms. They're not objects. They don't have an explicit lifetime. They're just coded numbers that represent some fixed thing in the runtime. The one you'll work with the most is a path. An XR path is a number that corresponds within that instance to a string representing a semantic path. When you create an instance, you first need to choose which extensions you want, very similar to how Vulcan works. In order to make an OpenXR application, you need at least one extension enabled, and that's a graphics binding extension. You can determine which extensions are all available on the system that you're using by using XR enumerate instance extension properties. However, if you don't have any optional extension usage and you can either run with the extensions you know how to use or not run at all, you can just proceed to create the instance and ask for the extensions you need. There's also a facility for API layers, as I mentioned earlier. These can be configured outside of your application through environment variables or similar to make the loader automatically load them. However, if your application wants to load them, you can enumerate which ones are available before you create an instance. Similar to Vulcan, there's an application info struct that you should fill out with your application name and engine name and version so that runtimes can identify your application. Then finally, XR create instance takes that information and hands you an instance handle. You use XR get system to find your desired form factor. OpenXR 1.0 natively supports without extensions stereo head-mounted displays, as well as handheld, mono, magic window style augmented reality. But not all runtimes will support both of these form factors of devices. So part of the startup process is asking if there is a system of the form factor you wish available. The form factor that you ask for might be available, in which case you'd get a system ID. It might be never available if the device that you're using can't do the form factor that you ask for. Or it might be temporarily unavailable if it's perhaps not plugged in or if it needs to transition to a different mode in order to be used in that way, if you have a device that can be used in multiple fashions. Once you have a system, then you set up your view configuration. This is where mono, stereo, or even more views come in. If you support more than one view configuration, you can use XR enumerate view configurations to find out which ones the system you've chosen supports to make your determination of which one you're going to render using. No matter which view configuration you use, you will then call enumerate view configuration views to get the correct number of views for your view configuration. Each view configuration has a fixed number of views. Mono has 1, stereo has 2. If you're using one of the vendor extensions, the XR Vario Quad views, that has 4, and so on. These are well known in the specification. Now that you have an instance, you can get your interaction set up, your action set and actions. Action sets are a group of related actions for a context, environment, and so on. You might have an action set called menu, or one called gameplay, one called driving. You can have one or more action sets active at a single time, so you don't need to have a game with car action set. You can just have game and then the additional actions in car. An action is a semantic or meaningful bit of interaction. It's something that you do. OpenXR focuses on the actions that a user takes in your application instead of on the buttons and controllers that are used to perform those actions. This is an important part of the hardware independence. There are several different types of actions. Boolean is essentially a button action. It has either on or off. There are float actions. Floats are things like an analog trigger. Vector 2 are two-dimensional floats, things like a thumbstick or trackpad. A pose is a special kind of action. That's a tracked object, so frequently these represent hands. And then haptic actions are an output action, allowing you to provide rumble feedback to the user. All these actions are created using XR create action. Once you've established which logical actions a user of your application will make, you'd like to customize how they actually perform those actions for the hardware that you're used to and that you're testing on. This is where interaction profiles and suggested bindings come in. For each controller type that you've tested, there will be an interaction profile. These are listed in the specification, and they cover a number of well-known devices. Additional interaction profiles will be added through extensions. Then, for each interaction profile, you submit pairs of actions and suggested bindings. These are the logical part of the controller that you'd like to use to drive that action. You can suggest multiple bindings per action in a call. For instance, both your left and right hands, and thus your left and right controller, could both trigger action grab object. The binding path that you'd like to suggest is an XR path atom, which represents a string like user hand right input select click. These are hierarchical strings. Here you can see that we are referring to the select button on what's being held in the right hand and the click of that select button. For the last two components, there are naming conventions and standardized names that are detailed in the specification. All these paths are listed in the interaction profile definitions in the specification. To make this a bit more concrete, I've gone through the sample Hello XR application that's in the OpenXR SDK source and compiled the actions and bindings that are used there. The Initialize Actions member function is where these get set up if you want to look at the source code on your own later. All these actions are in a single action set because the application is very simple. And all of these actions are specified for both the left and right hands. This uses the concept of sub-action paths. You can ignore this for the most part until later, but as soon as you want to be able to perform an action with two hands, but know which one hand actually did it, that's how you use sub-action paths. It's similar to the SteamVR input concept of restrict to device, if you're familiar with that at all. So the four actions represent a variety of action types. We have grab object, hand pose, quit session, and vibrate hand. So after creating that action set and those four actions, it's time to suggest bindings. And there are a number of calls in HelloXR to suggest bindings. I've picked a few of them for 3 different interaction profiles to illustrate some points. This first one uses the interaction profile KHR Simple Controller. This is not corresponding to any particular specific piece of hardware. It's a generic lowest common denominator sort of device that can be mapped to a wide variety of hardware. There are a few things to notice here. Overall, as you'll see as a pattern, the suggested binding path for the interaction profile, if it's under user hand left, then it goes to the sub-action path of user hand left, and similarly for user hand right. One point about the simple controller is that its select input is Boolean. It only has on or off. It has a click. So we're binding grab object, which is a float input, to user hand left input select click, which is Boolean. This is fine. The runtime will automatically convert that Boolean value to a float 1 or 0. There are conversion rules that are described in the specification for these common simple cases. The second example is the HTC Vive Controller. Here you can see that we've bound the grab object action to a different path. That's because the Vive Controller has those grip or squeeze buttons on the side, rather than a button simply labeled select. So the squeeze button, which is still a Boolean, like the simple controller, is now being suggested as our binding for grab object. Just as before, the Boolean will be converted to a float. And the last example of the suggested bindings is the Oculus Touch controller. Now there's a couple things here that are different. The Oculus Touch controller has a float squeeze input. It can say a floating value between 0 and 1 of how much you're squeezing. So here, the grab object action will get something that's not just limited to 0 or 1, but in that entire range. Additionally, only the left controller has a menu button. So in this case, we're only suggesting a binding for the left hand for quit session, which uses the menu button. User hand right, we're not suggesting a binding, and that's okay. The next major handle to create is your session. You'll first want to get your graphics binding ready. So depending on which graphics API you use, there will be a get something graphics requirements call that's specified by that extension. You need to call that before calling create session. This provides useful information how you configure your rendering in order to get the rendered content onto the display. You then create a graphics binding struct. These are also specified by the graphics binding extensions, and they're all chained on via the next pointer on XR session create info. I haven't talked about the next pointer too much, but similar to Vulcan, OpenXR structures contain a type field as well as a void pointer that allows you to chain additional structures on in a regular way. This is mostly used for extension functionality, but there are a few cases in the core specification where the next pointer is also used, and this is one of them. When you go to create a session with XR create session, that requires your system ID from earlier. And once you have that session, you then need to attach your action sets to it. to commit to the runtime saying, I'm all done setting up my actions and action sets and suggested bindings. I'm going to use them with this session, and I'm not going to change them anymore. This does make your actions and action sets immutable. You can't modify them after this point, and there's a special error code that you'd get if you tried to do that. If you happen to be writing an editor for a game engine, the solution for doing this, if you are editing your actions, is that each time you need to tear down the session, the actions and action sets, and then recreate them in order to modify them. This seems a bit like a pain, but there's an important reason for it. There's a reason that the action setup is done all up front. And it has to do with rebinding. We want to be able to provide the user with the maximum ability to configure how they're interacting with their application right away. So when they launch your application and it turns out there's no suggested bindings for the hardware that they have, the runtime can pop up a UI that provides them the ability to map your specified actions to the hardware that they have available. This happens behind the scenes and goes unnoticed by your application. If you were able to add actions and action sets later on during execution, not up front, it would then interrupt the flow of your application if rebinding needed to be done a second time. Additionally, if a runtime supports sharing bindings between users, you'd be able to compose a binding that supports all actions only if action setup is all done at once. Otherwise, if there's an action or action set that's only used in the last scene or two of your game, for instance, then a community-created and shared binding might very well be incomplete if that scene was not yet reached or was on a path that wasn't reached, making it less useful in general. To interact with tracked objects, you use XR space handles, and there are multiple ways to get these handles. Several spaces are known as reference spaces. You access these using your XR session and an enum. 3 of these are local space, view space, and stage space. There are additional ones added in extensions. Stage space can be considered a bounded standing area play environment. Local space is seated, and view space is essentially head space if you need to place something that's headlocked. To get an XR space from these enums, you use XR create reference space. Another kind of space is an action space. To create these, you use your XR session and a pose action. The result is an XR space just the same as with create reference space, so they are both examined the same way. For both of these types of spaces, session is the parent handle. Additionally, for both of these space types, you can specify an additional fixed transform at handle creation time. XR locate space is the call used to find the transform from one space to another. Note that you never just find the pose of a space, you always find a space with respect to another space. You don't track your hand, you track your hand relative to local space or stage space. To render, you'll need to create a SwatchChain. You'll obtain your graphics API specific formats through XR enumerate SwatchChain formats. You'll call XR create SwatchChain 1 or more times. Once you've created a SwatchChain, you'll access the graphics API specific handles or references to the SwatchChain images using XR enumerate SwatchChain images. This is a slightly unusual call. You'll pass an array of extension-defined structures. You'll want to save the information that comes back from this call to use every frame. It specifies in a graphics API specific way where to render your image to. Within the frame loop, there are 3 functions with frame in the name that control the life cycle of a frame. XRWaitFrame is a scheduling call. It blocks until the runtime determines you can proceed with head-pose dependent simulation and rendering. XRBeginFrame is executed by your application to mark the start of rendering or GPU usage for that frame. And XREndFrame submits the frame for display. XRBeginFrame and EndFrame calls must be ordered as if they were single-threaded, although they may be called from any thread. You'll populate the XREndFrame info display time using the output of XRWaitFrame. XRWaitFrame tells you when the next predicted display time is, and you'll use this in all your calculations and all your space locations. If your application is using pipelined or multi-threaded rendering, there are some more detailed timing requirements that are important to know. You can have at most 1 simultaneous XRWaitFrame call being executed at a time, and each XRWaitFrame must eventually be matched with a unique XRBeginFrame. They come in pairs. Each waitFrame has a beginFrame, and every beginFrame has a waitFrame. Additionally, any XRWaitFrame call will block in the runtime until the previous frame's XRBeginFrame has been made. Between begin and end frame, once it's time to actually render, you'll need to use the SwatchChain that you created earlier. XRAcquireSwatchChain image does not give you permission to write to the image, but it does get the index of the SwatchChain. XRWaitSwatchChain image must be called before writing to that image. It's typically called immediately after acquire. However, you may, as an optimization, look up or create your command buffers using just the index from AcquireSwatchChain image before blocking on the compositor releasing the image for writing to your application. XRReleaseSwatchChain image is what you call when you're all done rendering, right before calling XREndFrame. XREndFrame implicitly uses the most recently released SwatchChain image for displaying to the device. When you're doing your rendering, you need to render for the predicted display time and for the pose that the head is anticipated to be at that time. XRLocateViews is how you look up that information. It works very similarly to XRLocateSpace. Now that we have an application that can render, we probably should look into getting input to make it interactive. XRSyncActions should be called once per simulation frame in your application. It specifies which action sets should be active for that frame and updates all non-pose input data in those active action sets. After you sync actions, then get the data. Any action set that is attached but not specified in the most recent XRSyncActions call will have the actions return not active. Actions additionally might not get data if your session is not focused for privacy and security purposes. To get action data from actions, you'll use XRGetActionState calls. There's one for each type of action. Pose actions are a little bit different. They continue updating all the time, not just at XRSyncActions time, because tracking is latency and time sensitive. To get the data from a pose action, you'll usually just create an XR space for it and then use XRLocateSpace. only the active-inactive state of a pose action is controlled by XR sync actions. Typically, you'll process most of your input either before you call XR wait frame and XR begin frame, or after XR end frame. There is a per instance event queue that contains a range of events. This queue must be polled on a regular basis. Typically, once a simulation frame is a good idea. XR poll events requires an instance. However, many events only happen during a session. These events can describe changes to the active interaction profile, continuity of reference spaces and tracking, changes in the session state, and other things. You provide an XR event data buffer to XR poll events, and the runtime populates it with an event of some other type. You have to make sure you set the type to XR type event data buffer, and then when you get it back from that call, check that type value and reinterpret that structure accordingly. Thanks for your time. Hopefully you found this introduction to OpenXR and exploration of the structure of an OpenXR application to be helpful. I've put a number of resources on this slide that you can follow for additional information. If I'm not available for questions at the time that you're watching this, please feel free to drop by one of the community locations for the OpenXR group and leave a note there with your question. I or someone else in the community will be happy to respond.